Or can people hear me or see my screen? Okay, there's a yes. Awesome. Awesome. Cool. Okay, so there were several questions posted on Piazza, so I'm going to go through these first, and then we can answer questions as we go along, like normal. Or does anyone have any general questions about the final right now before I just start working through some problems that you would want to know? Like general information, not a specific question. All right. So the first two are a couple questions from the, I think the plus final exam practice sheet that was handed out. So they wanted me to go through a couple of these problems. One of them was number 15, and it's asking what is the final exam expected from the following reaction sequence. So we start with a chloro-nitrobenzene, and we're going to react with iron HCl. This is a workup with sodium bicarbonate, which will be essentially just a mild base. We're going to add in bromine and water, then sodium nitrite with HCl, and then finally hypophosphorus acid. So the first step is a reduction. This is a reduction reaction of nitro groups. We have several of these. There's also the zinc amalgam that will reduce them. Zinc acid reduces nitros. Tin chloride reduces nitro groups. And you can also hydrogenate nitro groups. So for the first product will be the conversion of the nitro group to an aniline, an NH2. These are done under acidic conditions. So actually I should probably say that the first step, this will be protonated. And then in the second step, this molecule just gets deprotonated to its neutral form. We can take care of that pretty easily. Our third reaction now is bromine and water, and these are conditions that are notable because here there is no Lewis acid. So usually bromine on its own won't be able to do electrophilic aromatic substitution on a benzene ring, with the exception of when there's very strongly activating groups on the ring, like the case when you have an aniline or like a phenol. And so usually you can't control these because these react so quickly with bromine. So this will do electrophilic aromatic substitution. We can imagine the mechanism generally going, I'm going to draw the bromine over here, so it works my double bond a little better. It opens. We're going to make an arenium intermediate that is stabilized by the lone pair on the nitrogen. So you can imagine this nitrogen pushing into the ring because this is going to get you directly to the correct resonance structure. Even though there's a chlorine on the ring, this is a much weaker directing group than the aniline. We always want to have it go by what is the strongest directing group on the ring, and that'll determine the regioselectivity of the electrophilic aromatic substitution. You can have the bromine ion come back to regenerate aromaticity. This will happen twice, so we're also going to brominate the other side afterwards. So I won't write out the mechanism, I'll just write Br2. I'll try to write excess bromine if I were writing in Sonotest just so that you know that it will go on twice. But this generally happens whether you want it to or not. The next step is sodium nitrite and HCl. This is to make a diazonium. So this will convert our aniline into the N2 plus form. Normally this is not isolated but used directly in the next reaction. And we have this long list of reagents. Most of them have copper. Yeah, usually it's just bromine. It's a combination of bromine and water is usually what you'll see as the reaction condition, and it's on an aniline or a phenol. If the para position were available, it would also continue to react here as well, but we already have a chlorine, so that's blocked. So I think the example in the notes has it going all three at once, and it's like 99% yield or something. So this diazonium is not isolated. And again, these mechanisms go through radicals. And so note that this is hypophosphorus acid. This is not phosphoric acid, so it actually acts as a reducing agent. And this will just turn the diazonium group into a hydrogen. For most of the examples we have, it's copper plus something, and then copper will just whatever is the counterion to copper, that gets put on where the diazonium is. The two cases where we don't need copper are iodide. Iodide is highly polarizable, and you'll put an iodine there. And this is the fairly special reagent to convert the diazonium into a hydrogen. What about chlorine? Chlorine is more reactive than bromine. If you added in chlorine, it would also chlorinate everywhere. And it might even be a little too reactive, but for this class, so we just say it chlorinates. Even iodine would be able to do these electrophilic aromatic substitutions quite easily without too much acid activation. So this is how we get to the final product, which looks like it is D. And I think they provided solutions to you guys as well. So make sure that no, I'm almost positive I'm right. Yes. The next question is something from the most recent topic area. We have a mixture of sodium ethoxide and ethanol. The first thing we always want to do is check that we have ethoxide to match with our ethyl esters. So we're good there. We don't need to go and check to see if there's going to be any unwanted transesterification. Oh yeah, I mean, I always recommended people use, so the question is, do we need to know the reagents to reduce nitro groups? And I guess that's a yes. They are, all of them are listed out, I believe, on the topic sheet review. So like the list of topics, I think I have in parentheses all the ones you would need to know. I always encourage people to use tin chloride in a synthesis because that will have the less reactivity problems with other functional groups. Usually tin chloride won't do anything but reduce a nitro group, whereas palladium on carbon may hydrogenate double bond, or something like zinc amalgam will also reduce aromatic ketones and aldehydes. But getting back to this problem. So then we have sodium ethoxide. We don't need to worry about transesterification, but this is going to act as a base. So we have two potentially acidic hydrogens in these molecules. We have this hydrogen, which is acidic due to the double bond that would put the enolate into an extended enolate of the ester. This is going to be much less acidic than the 1,3-diester. So we're going to have sodium ethoxide deprotonate this malonate first. Malonate enolates are very delocalized, so they're going to be extra soft. And it's going to be able to react in a 1,4 fashion with the alpha-beta unsaturated ester. So this will be a Michael type addition. And I think a key in this problem is, keeping track of our carbons, because connectivity will end up being important for choosing the right answer in the end. So we have one carbon that's attached. We'll go directly to the enolate initially. And there is a methyl group on the carbon that the enolate attacked. This will then grab a proton either from another malonate or another ethanol molecule. Oh, I always like ethyl esters better, or methyl esters. And this will be the product after the first reaction. The other types of reactions you may consider if they were still able to keep going would involve deprotonating one of these two groups. Most likely under the basic conditions we would deprotonate this hydrogen, but we'd reprotonate that again on workup. When you add more sodium hydroxide to this, we're going to hydrolyze all of the esters. So I'm just going to write NaOH. We're going to have H3O plus. We still have this methyl branch. Actually, I'm going to, and now whenever we heat this up, we'll lose carbon dioxide. It'll enolize, and we'll tautomerize. We have 1, 2, 3 carbons in between with a methyl group on the inside. And this is what we'd expect our product to be. And that should be product E. Yeah. This looks right to me. Boom. So I think the big idea here is recognizing that this is going to be a malonic ester synthesis. The difference is we're not doing an alkylation with a normal alkyl halide electrophile. We're relying on the Michael addition now to do the 1,4 conjugate addition into this double bond. Here's another question. And I believe they asked me to kind of walk through all the individual steps. This is a combination of 2 different name reactions. The first step is called the Arbuzov or Arbuzov-Michaelis reaction, followed by the Horner, Wadsworth, Emmons reaction. Or HWE, and this one is similar to a Wittig reaction. So first we can take a look at the Horner or the Arbuzov step. This is to make phosphonates, which are the reagents we need to do the HWE. We have this alpha bromoketone, and this is going to be very electrophilic. And we have triethyl phosphite. So phosphines and phosphites are fairly nucleophilic. You can think of them reacting a lot like nitrogen in a lot of ways. So this is going to be able to do an SN2 on this bromide. So this is the sort of unintuitive step, or one that I think people miss or forget the most. We're going to end up with a positively charged phosphorus. We have a bromide anion that's hanging around, and it can actually do an SN2 reaction on the carbon of the ethyl to give more electrons down to the phosphorus. So this will give the phosphorus more oxygen bonding. Phosphorus always makes strong bonds with oxygen. If you want to leave this as a plus minus, where a positive charge on the phosphorus and a negative charge on the oxygen, that is just fine as well. So this is the product of 1. In the second step, we're going to add in sodium hydride. Sodium hydride is always a base. Hydride on its own, sodium hydride will never act as a nucleophile. And now we can kind of see that this is going to be a particularly acidic hydrogen, because not only can we make this enolate that's going to be stabilized by this oxygen, we also have this electron withdrawing group of the phosphonate on the other side. You could also just draw this as keeping the charge on carbon if you want. And then we're going to add in the aldehyde. So this is now going to look a lot like your aldol type addition. Unlike the Wittig, these are usually viewed as being stepwise and reversible. So first we do an aldol onto the aldehyde. This gives us an intermediate alkoxide. And this phosphorus still wants more oxygen bonds. Bond looks weak. We can imagine adding in. I'm running out of space. I'm going to move this up. Make it a little bit bigger for everyone to see. Now we have this four-membered ring with a phosphorus and an oxygen. So similar to the Wittig reaction, this will just break apart where phosphorus is going to get even more oxygen bonds. And out comes a double bond. So if you go back to the solution, I said that this is E-selective. So usually the thermodynamic product results. That's because these addition steps are reversible. So it'll be able to sort of go back and forth until it gets to this lower energy conformation, which implies that these two groups are actually on the opposite sides of one another. But if you just remember that it'll end up being trans or E, then you should be good to go. The Wittig usually isn't as selective because its steps are less reversible. All right, moving along. They were asking, why would this not be selective or not successful? And so the goal was to be making Grignard reagents. So the first one makes a Grignard reagent, the one below makes a Grignard reagent, the one to the right makes a Grignard reagent, but D would make a Grignard reagent initially, but there's incompatible functional groups. So I have this arrow drawn from this Grignard because it could do an intramolecular attack onto this ester. So we would expect this Grignard not to be a stable Grignard. It would actually keep on reacting to eventually make this ketone. The question is whether it would give a product ketone or another one of these Grignards would do an intramolecular attack. I wouldn't ask you guys that. Ketones are more reactive than esters, but intramolecular reactions are also faster. Intramolecular would probably win here. And this would be after the initial tetrahedral intermediate, of course. But you don't need to worry about that. You just need to know that some sort of side reaction would occur. If the ester was a ketone, then that would not work because you could still do the same attack. You wouldn't get an actual Grignard afterwards. You would end up now with a tertiary alcohol because you don't have a leaving group. So after workup, you would end up with the tertiary alcohol here. Just crushing it. We're going through them. Okay, there was a question about this problem, and the request was for the first step of the problem to be further drawn out. So this first step is the conversion of this cyclobutanone into this gamma lactone. So this is the Baeyer-Villiger reaction. And depending, sometimes you'll see this being catalyzed in different ways. I like to think about it as this per acid, because you can do it under acidic or basic conditions. If they're just neutral, this is a reasonable mechanism. We need this per acid to attack into the carbonyl first. So you can imagine having the acid protonate this carbonyl. Then the anion will be able to come back to react to make the tetrahedral intermediate. Now this is where the sort of tricky bond shift comes into play, where we get the ring expansion. Oh, I wasn't drawing the methyl. What am I doing? I'm not even drawing a cyclobutanone. Let me redraw some of these. My apologies. We have a cyclobutanone with a methyl. This one's ugly. We don't want ugly. We want beautiful molecules. I'll answer the reduction question for the next step after I'm done with this. Sometimes you see this under acidic conditions, you'll have the leaving group activated beforehand. I'm fine just drawing it this way as long as we get the bond migrations right. So the key here is that we have this weak oxygen-oxygen bond. And this oxygen-oxygen bond means the acid will be a good leaving group. Good leaving group. In order to have this bond leave and break, we need to have the electrons go to the acetate. That'll stabilize the negative charge well. That means we need to have a nucleophile. Turns out we have this nice sigma bond here that is in the correct anti-periplanar alignment to interact with the sigma star of that sigma bond, so that this will be able to do a 1-2 shift. The 1-2 shift will lead to formally a carbocation, but it's a carbocation next to this oxygen, so the electrons for the oxygen can just come down. It will go to stabilize the positive charge. Then you can have the acetate come back and grab the hydrogen. So in the bond migration step, you could have had either side really go in the bond migration. Geometrically, the peroxide could have twisted either way to either side. There ends up being, during this migration, you end up building up partial positive charge on the substituent that migrates. And so that ends up making the more substituted carbons generally the ones that migrate first. So we'd expect the one that is the methyl connected to be the one that also migrates and gets attached to the new lactone oxygen. So I think the next question is, how do you know it would ring open? And this has to do with the reduction step of lithium aluminum hydride. Sodium borohydride would not work here. Sodium borohydride will not reduce esters. It only reduces ketones and aldehydes, or things even more electrophilic like acid chlorides or anhydrides, and we'll see that in a minute. But if we go through the mechanism, we can see why we're going to have this ring opening take place. We're going to have the aluminum hydride act as a sigma hydride nucleophile to add into the lactone. This will make a new tetrahedral intermediate with now this O minus. And these tetrahedral intermediates always collapse quite quickly, and they're in equilibrium. So this will be ring opening, and it'll be in equilibrium. Perhaps it's not even a favored equilibrium because it is a cyclic acetal, but there is some equilibrium there. And as soon as you end up ring opening this aldehyde, or ring opening this hemiacetal, we're going to make a new aldehyde that is also very reactive with lithium aluminum hydride. And we're going to end up making the bis alkoxide afterwards. And from there, it gets worked up to the alcohol. that gives us this alcohol. PBr3 turns it into the bisbromide, and the sodium cyanide will do a double SN2 reaction. Lithium aluminum hydride will always open a ring if it is a lactone. Sodium borohydride, if there were a ketone, there's no good leaving group on the ring. So that these would, regardless of the reagent, will only give you the alcohol afterwards, because the intermediate O- still needs to have a reasonably stable leaving group to kick out, and you would not be able to kick out this carb anion, for instance. So the reason the ring opens is really because this oxygen is here, and it is a decent leaving group under the reaction conditions. I think the other type of functional group we had that was able to ring open were in cases of, with sodium borohydride at least, or when we had something like an anhydride like this. And it'll either go to an alcohol and an acid or a diol, depending on whether or not the reducing agent you use can reduce the carboxylate. So if it's lithium aluminum hydride, it'll go to the dialcohol. If it were sodium borohydride, the carboxylate would leave, it'd still be attached to the molecule, and it couldn't reduce any further. Now we have a series of questions. This goes back to, maybe this is topic 2. So it's asking which is more. Yes, that is the next question I will get to. I think you posted that on Piazza, so we are almost there. We are getting to whether or not sodium, and yes, sodium borohydride can reduce these. I can talk about this more explicitly in a moment. So which is more basic, a Grignard or methyl lithium? We're going to say in this class they are the same. Because while magnesium is a little bit more electronegative, we have this bromine here. We're not sure how that's also influencing that counterion. So I would say for reactions between Grignards and organolithiums, treat them the same. I won't ask you which one is more basic between those two. You mainly need to know that all of those like very strong things like sodium, lithium, Grignard. Grignard is probably still a little bit less basic, but the reactivity is essentially the same. It's zinc where you get the big jump to something that is much less reactive. So I would say that, yeah, you'd probably say Grignard is a little less basic, but for all intents and purposes, we treat them pretty much as carb anions. And yeah, I would say treat them the same. Definitely with acid chlorides. Nitriles, you don't see organolithium additions to nitriles as much. I think it's because it has something to do with the nitrogen-magnesium bond being a little stronger, but we'll say the same. These are little distinctions that we never discuss, and for right now, I would accept either answer. The methyl lithium with an acid chloride would end up making a tertiary alcohol where 2 methyl additions would occur after you kick out the chloride. And with nitriles, you would end up making methyl ketones. So the question was, can anhydrides be reduced by anything, or can they only be hydrolyzed? So there's a number of nucleophilic additions to anhydrides as well. The ones that we really talked about in class as far as reductions largely pertained to these 2 cases. I kind of filled out the chart for the reduction reactions just because, well, I didn't want to leave just an empty space there. And so the ones with sort of asterisks are more or less like, you don't really need to know this. Oh, I updated this. I think it's correct online. I grabbed this from an old version. That's one you definitely need to know. Acid chlorides get reduced to aldehydes. I actually don't know. I've never seen anyone try to reduce an anhydride or an acid chloride with sodium borohydride. There's not really a good reason to do that. So I don't even know. But in this case, yes, you will be able to reduce anhydrides. They either go to diols or they go to 1 alcohol and 1 acetic acid if it were this type of anhydride. So we can walk through this a little bit. So first we're going to have, I'm just going to say metal for now. So where metal is Al or boron. I have a hydride addition to the anhydride. Remember, anhydrides are more reactive than esters. They're more along the same lines as like a ketone, so we can reduce them. We're going to make a tetrahedral intermediate that now has a good leaving group. So these acetates are going to be very good leaving groups. This will be able to go down and leave. Along the way, we're going to make a new aldehyde. And this leaving group. So in either case, either one will be able to further reduce this after workup to the alcohol. Lithium aluminum hydride can reduce carboxylates all the way to the alcohol after workup, whereas sodium borohydride would not be able to react with this. So in the case of sodium borohydride, we get one half of the molecule completely reduced, and the acetate just goes to acetic acid in after workup. And lithium aluminum hydride, it just reduces everything, and both get turned into alcohols. In the event that you have a cyclic anhydride, and you were to react this with sodium borohydride, now after workup, you'll end up with the acid attached to one end. Oops, I forgot a carbon. And the alcohol on the other. So now it's the same sort of reaction, only both of the products are attached to each other because they were initially linked through this carbon-carbon bond. So there's a question of why can't diol reduce a carboxylic acid? I thought it could reduce a carboxylic acid to an aldehyde. So diol can reduce esters. Oops. So no. Esters go to aldehydes. Carboxylic acids would largely just be deprotonated. So if we think about how this reaction could work and how diol as a mechanism works, as you kind of mentioned that it's neutral, so I wanted to maybe talk about diol a bit more right now too. We have the molecule diol. In addition to it just being neutral, it's really a Lewis acid, right? Because we have this empty p orbital. And so before it can do a reduction, it needs to coordinate to some sort of, either nitrile or carbonyl group first. So if we have a carboxylic acid come in, it'll first add its electrons into the aluminum. The aluminum will gain a formal negative charge, making this hydride more nucleophilic and more hydridic, but it also makes it much more basic. In the case of the oxygen, now this carbonyl becomes much more electrophilic, but it'll also increase the acidity of this hydrogen even further. So rather than this hydride, I'm going to do two different colors. Instead of it going and attacking this carbonyl, instead, it's going to go and just take this hydrogen, because then we can go and get its charge returned. This is just going to be a deprotonation. And you're going to make the aluminum carboxylate. And now we're going to have And now even if another diball tried to coordinate to this carbonyl, now it's too hindered because the other diball has these big isobutyl arms that kind of block it from making a strong coordination. And the MDP orbital is also probably taking some electron density from the lone pair on the oxygen, reducing the Lewis basic nature of this carbonyl as well. So the main significance is just to understand, I guess, how the mechanism must change and how the mechanism must be different between those two situations. Instead of it being a direct nucleophilic attack on a neutral carbonyl, you're just going to have a complexation first. The other part being because of this nature, after the addition to make a tetrahedral intermediate, we don't really have a strong anion. It's that aluminum-oxygen bond that is fairly stable and helps to stabilize that tetrahedral intermediate to go to aldehydes. So I would say if I had to list two things, the two main points here are mechanism, and this means complex formation, then hydride attack, and two, esters to aldehydes. I'd say these are the two main differences. I guess you could also say nitriles to aldehydes as well. So there are some unique reactions that diball will be able to do. But I always try to get the idea across of the mechanism because it helps to explain some of the reactivity afterwards for these specific reactions that take place. Okie dokie. We have a question of how does this last step work with sulfuric acid? They were thinking that sulfuric acid could do an acid-catalyzed dehydration that caused the primary alcohol to be replaced with a double bond. But how would the tertiary attack the double bond to close the ring? So it is possible. There's actually a number of equilibria that could be at play. The dehydration of a primary alcohol is actually going to be very, very slow. We saw that sulfuric acid with like very, very high heat could take ethanol to ethylene, but that was a fairly special case, and that usually leads to a lot of problems. If you were to protonate this tertiary alcohol, this is going to lead to a much faster formation of a carbocation. Remember, the primary carbocations don't really form very easily. They require a lot more energy. And in this case, usually they would be displaced or eliminated through more E2-like pathways. Protonation of a tertiary alcohol, though, will lead to relatively fast formation of a carbocation. And this could do two different things. This could eliminate to give the double bond. That is possible. And it could give any of those potential double bonds. But the protonation will be reversible under acidic conditions. So either way, we're going to keep going back to this same tertiary carbocation. And this is going to be expected to be a fairly fast process that will be favorable is because this alcohol that's on the same molecules as tertiary carbocation will be able to make a 5-membered ring. So molecules always like to form rings entropically, or at least 5-membered rings are kinetically fast. And so this will be able to first make the protonated alcohol, and then we could have some other molecule, maybe it's another alcohol, or it could be sulfate. We can just say base for now. Some sort of base will be able to take this proton away. So the tertiary alcohol doesn't actually attack anything. It gets turned into the carbocation. So this is one of the extra practice solutions, I think, from exam 3, maybe. I said, what was the giveaway here for us to know to use a Wittig reaction? Also, how did methanol get attached to the double bond? So I think the way you know it's a Wittig is actually by recognizing the reaction you need to use to make this type of functional group. So this is goes back to haloetherification. And so this just kind of requires the recognition of having an alcohol next to a bromine. And this actually implies a certain type of reaction. So MBS is pretty much the same as bromine for how we use it. So we can just say bromine as well. Let me make my 2 look like a 2. And so this will arise retrosynthetically from a bromonium. In which we're going to have bromine and methanol added to the double bond. And with methanol as a solvent, so there's going to be a lot of methanol around. We know that the bond is going to weaken towards the more substituted carbon because it's going to be better at stabilizing positive charge. So really you can draw this maybe a bit more realistically as thinking about the bond as having a bond to bromine and this longer, weaker bond that puts partial positive charge on the bromine and partial positive charge on the carbon. Sorry, my molecule art is not great today. And we'll be able to attack this center ring open and will give us this halohydrin. So this naturally comes back to a double bond intermediate. And since you needed this intermediate, the use of a Wittig makes sense here. Trying to do another approach besides the Wittig to convert this ketone to this double bond might actually be pretty hard, because if you did like an ethyl Grignard attack followed by elimination, we don't have a strong preference for which of the double bonds would form afterwards, because you could have made the double bond there or there, and they would all be tri-substituted. And inside the ring actually might be a little bit more thermodynamically favorable. And so this is really a reaction. If water was the solvent, then you'd end up getting an alcohol instead of methanol. We reviewed this a bit in the alcohols and ethers section. And this is, I think, one of the first reactions listed on the reaction summary page for the early topics. And there's also going to be a stereochemical implication for how the methanol attacks to ring open. But since this cyclohexane is symmetrical, you can't really tell based off of the molecule is drawn. All right, we've made it to the last of the Piazza questions. So I mentioned this one a bit, but there was some commentary on this as well that didn't get copied. Let me go over. And the question was confused between A, C, and E. If you pulled off a hydrogen that is alpha to the carbonyl, wouldn't you get an enolate that has resonance in all 3 cases? Why is the hydrogen attached to the nitrogen in E the most acidic one? Mainly it comes down to the type of resonance structure you have and the number of them. So in this case, the pKa of enolates are generally across the board fairly high. They're like for a ketone, they end up being, in the 19 or 20 region. The one case where we did see an imide in class in this topic was in the Gabriel synthesis. And we could use actually pretty weak bases like hydroxide to go and take this hydrogen away because it gets this resonance delocalization. I think to make a comparison between a normal type of enolate and these other structures, you can also just, let's take E for instance. this would end up putting this negative charge on an oxygen or a carbon. Whereas in the case of the imide, we can put it on two different oxygens or a nitrogen. And so not only do we have two additional atoms, we're sharing that charge around two. The nitrogen in addition is also going to be more electronegative than your carbon. So that is how I would be looking to answer this type of question. I was mainly thinking people would recognize E as being a subset of the Gabriel synthesis and using that sort of as a reference and a guide. But it's really being able to share that negative charge across three different heteroatoms. Yeah, and that sort of logic follows as well. So just like the 1,3 dicarbonyls is able to, they've become much more acidic. You get a similar jump in acidity going from, say, 25, from B to E. E is much more acidic than B because just like the case of this hydrogen in the middle, it's sort of now it's like the 1,3 dicarbonyl of amides and imides and stuff. Cool. All right. There is a question on Piazza. I don't know if they intended for me to discuss this. This has to do with the extra credit problem, number 1. Confused exactly where to start or continue. I know I need the epoxide to open organolithium tertiary alcohol. We could talk about that. We're going to post those solutions pretty soon anyways. And I realized I just wrote out an answer that someone wanted in class that was about these as well. So maybe I can kind of comment on both of them at the same time. I think I wrote out fairly clear instructions on Piazza, but I must have missed that they wanted me to discuss it in class. So to whoever that was, I apologize. I believe the question they're talking about is this one. I think this is number 1. We have methyl iodide, and this is going to oh, no. I should look at what I'm drawing as I draw it. To this tertiary alcohol. And so there's a couple of things to look at. One, we can go and map out our usual cases of where do the methyls land. We can see where our cyclohexane started and ended. And now we can also see where, what color have I used? I'll use a red. Where this alpha bromo ester came from. And so part of this is a bit on, order of operations, thinking about what would be the best order to do things. So since we see that we have an ester here and we have 2 methyls introduced to the product, we could think somewhere this needs to be turned into like methyl lithium. And perhaps it would eventually be attacking this ester to add twice to make the tertiary alcohol. Another way to, so if we did that at the very end, we do retrosynthetic analysis. That would have this type of reaction take place. But now we kind of have this question of what will happen? Will methyl lithium attack this ester, or will methyl lithium go and attack the less substituted site of the epoxide? And that's a good question. It's pretty hard to determine where methyl lithium will go. But we also have some other options, right? Because we have this epoxide. No matter what type of reaction you use to make the epoxide, we always go back to a double bond. So if the last thing we did was to make this double bond, and this would be like MCPBA, then this would not be as bad of a problem because we know that MCPBA will not hurt a tertiary alcohol. Now we can use our same approach to add in these two methyl groups at the same time with, say, methyl lithium. Because methyl lithium now has the choice of adding 1,2 or 1,4. But we know that methyl lithium and all organolithiums are hard reagents, and they do not add in the 4 position. They'll do a 1,2 attack, and the intermediate ketone as well. So now this leads us to trying to make this double bond in the middle somehow. And when we see alkyl halides and ketones, we should be thinking about perhaps using a Wittig reaction. So that is a great way to make. You potentially could also do this with the Refermatsky reaction, where you're turning the alkyl bromide into an organozinc, followed by E1CB elimination. But I like the Wittig reaction. That means we need to go back to our starting cyclohexanone. And we need this ester, or this Wittig reagent. And the Wittig reagent will come back to a phosphonium salt. Which comes back to our last reagent, the bromide plus triphenylphosphine. We have a question. Can methyl iodide stay as methyl iodide, or should we do a halogen swap to get methyl lithium? You should, if I give you methyl iodide, I want to see you add lithium to this to make the methyl lithium, or add Grignard to this to make the methyl Grignard. Can esters undergo alpha halogenation? Yes, they can, but I would make one comment on the kind of reaction conditions you would need to use. Because, for instance, whenever we do alpha halogenation of, say, a ketone like this in class, usually we write Br2 and water, right? And, oh, sorry, sodium hydroxide, not water. And this would lead to alpha bromination. In this case, we'd only brominate twice, so the haloform reaction wouldn't take place. If you had an ester, we need to think a bit more about this base. Because if you have an ester and you wanted to do, let's just put the ester on this side, and you wanted to do the same alpha halogenation, the hydroxide would want to attack this ester and hydrolyze it before it could do the alpha deprotonation. So this is something we would not want to have happen. So we just need to use a different base. In this case, LDA can be your friend. You could say 1, LDA, 2, add in bromine. People use NBS here too. It actually works the same way. And this would let you make a monobromo. You could repeat, and you could put on the dibromo. There are some stronger organic bases that could probably affect the non-nucleophilic organic bases that would also perform this. I don't know if you guys learned about DBU and Organic 1. That one might work. There's stronger ones you almost certainly didn't learn about. But yeah, that totally works. We can draw that out. So what happens to the ethoxy group? So I'll draw out this step a little bit more clearly. So methyl lithium will attack. Oh, and then I'll comment on the use of zinc. So methyl lithium will attack, will make this tetrahedral intermediate. The ethoxide will quickly leave. This gives us a methyl ketone, and now this methyl ketone is more reactive than the initial ester. So now a methyl lithium addition to this ester will go and make the tertiary alcohol after workup. So this is another option you could do. So this is the Refer-Matsky reaction. Actually, I'll bring this in next. So we learned that Grignards and esters are incompatible, but we learned that organo-zinc compounds are actually just fine. So we could use zinc metal to make a stable alpha zinc compound. In a lot of ways, this type of organo-zinc is a lot like an enolate. And because it is like an enolate, also tells us why it is going to be more compatible with the conditions. But the zinc actually stays more on the carbon than the oxygen because of its more covalent nature. So this will be able to do the addition into the ketone. To work up, we would imagine making a tertiary alcohol. And so you'd probably want to add in one more step with ethoxide to affect that E1CB reaction. Now, let me move these all up a bit. I'm running out of space. I'll just erase that line. And you can view this as, a negative charge on the carbon or on the ester as an enolate to be able to go down and kick out the hydroxide. So it is player's choice. One of the beauties of this point of the class is usually there's more than one way to do something. Cool. Got any more questions? I don't see any new ones on Piazza. I don't see any more questions on the chat feature. In that case, I may let you guys go. Have a good evening. Happy studying. Feel free to put up some more questions on Piazza, and I can either answer them directly, or I can walk through them in the office hour tomorrow night. Same time, same place.